The study of projectiles, objects flying through the air, is a common theme in most physics courses. Many courses spend a substantial amount of time on this topic. We'll discuss it now, but we won't spend so much time on it because, although you may not realize it, we've already solved this problem. Our discussion here will also serve to illustrate two larger points about solving motion problems. One, using the computer to help solve problems is really powerful, so let's do that whenever we can. And two, the models of motion we built earlier can be used to solve new problems, so let's keep them in mind when we run into new motion situations. Here's a typical projectile motion problem. A ball with mass 1.5 kilograms is thrown with an initial velocity vector as shown at time t equals 0 seconds from the origin. Air resistance is negligible. A. When does the ball reach its maximum height? B. What is the maximum height above the origin? C. How far has the ball traveled horizontally from the origin when the ball is at its maximum height? At first glance, this might look like a new problem for us. For instance, we haven't dealt with thrown objects that move in more than one spatial dimension. However, let's look at this starting as usual from a fundamental principle, Newton's second law. The statement of the problem suggests that the thrown object has only one interaction with its surroundings, the weight force exerted on the object by the Earth. We already handled a case that has exactly the same physics, the falling object we discussed in detail in an earlier lecture. This suggests we can use the model we built for the falling object to solve this problem. Let's do just that. We'll start with the completed computer model for the falling object and modify it to solve this problem. You'll soon see that we will have very few changes to make. Let's start with the system properties and initial conditions. Here we have a ball with mass 1.5 kilograms, so we need to put that in. Also, we need to specify where the object is when we start doing our predictions. Here, the object starts from the origin, so that's already correctly specified in this code. Now, recall for our falling object, the object started at rest. However, for the thrown object, we're told that when we start looking at the object already has a non-zero velocity. That's an initial condition, so we have to put that in here. Notice all the throwing that got the ball to the current position with this velocity happened before we start making predictions. So we don't need to put in the force of the throw or anything else that happened in the past to the object. The initial conditions take care of all that past history, all the way back to the Big Bang. From the moment t equals 0 onward, the ball is released, and the only interaction we have is the weight force, and we already have that in our model. Note for this problem, we need to make sure we set our drag force to 0. We can do that by simply setting the constant b to 0. That's all the physics we need to change because, as we said before, our model already contains correctly Newton's second law with just the weight force as the net force. We will, though, make two more changes that will help us view the results. First, we need to adjust the arrow scale so that the arrow we draw to represent the weight force is a meter or so long and fits the visualization window. We'll choose arrow scale to be 0.1 newtons per meter. You can verify that that is a reasonable choice. We also want to print out the predicted position and velocity for a range of times as the computer model runs. To do that, we're going to put a print statement inside the loop by indenting the statement like this and specifying as shown that we want to print the time, the ball's position, and the ball's velocity for every pass through the loop. Now we're ready to run our computer model. Here's what the motion looks like. The yellow arrow represents the weight force on the ball. The predicted positions, velocities at different times show up in our output window. We just need to scan through the list to find the maximum height and the corresponding time and horizontal position. That's it. We're done. Problem solved. Now, a problem like this also happens to be of a type that we can solve using pencil and paper, which is the approach many people think of when they think of solving physics problems. This is called solving a problem analytically. We'll show how to do that approach here, but using the computer to solve the problem is fair too, and in fact is much more powerful, especially if we want to solve problems that are more realistic. For example, if we want to solve for the motion of this thrown object with the modification that we also want to include drag, say by using the drag force model we used earlier, we could do that simply by choosing a suitable non-zero value for the constant b. This would cost us hardly any additional effort. However, if we wanted to solve the problem analytically with both weight and drag forces, that would be substantially more difficult than simply solving analytically the problem with just the weight force. Let's first discuss in detail the analytic case with weight only, and at the end, we'll outline briefly what we would need to do to include weight and drag in solving the problem. We're going to use calculus to solve this problem. The problem can be solved without calculus, but we'll leave that as a topic for discussion on the class forum. Recall we said earlier that our motion prediction using the computer was equivalent to performing integrals to determine the velocity and the position as a function of time. Let's write out the first integral, which is just the integration of Newton's second law, expressed here in component form. We see that the vector equation is nothing more than two scalar equations, one for the x component and one for the y component. Let's look at each component in turn. First, we see the x component of the velocity is constant. That makes sense because the x component of the net force is 0. The weight force, which is the only force, has no component along the x direction. So 0 net force along x means no velocity change along x. Thus, v sub x is constant and equal to the initial value. The y component of velocity is a different story because the weight force is non-zero along y. So we need to put that in and do the integral, which is easy because the weight is constant in time. So we end up with the integral of dt from t equals 0 to some final time t, multiplied by the constant minus g. We do the integral, and now we have the final result for the y component of the velocity as a function of time. So, at this point, we know everything about predicting the ball's velocity. We now turn our attention to the second integral, which predicts the position vector of the thrown object as a function of time. Here it is in component form, where we need to use the result we just obtained for the vector velocity. Again, we can look at each component in turn. First, for the x component, we need to add to the initial x position the integral of the x component of the velocity from t equals 0 to the final time t. v0x is constant, so we can do this integral easily, and here it is. So now we have the x position as a function of time. Now for the y component, we need to add to the initial y position the integral of the y component of the velocity from t equals 0 to the final time t. It's a little more involved to do this integral, but this is still elementary calculus, so we can do that, and here's the result, and now we have the y position as a function of time. So, to summarize, we now can predict the motion future for the ball because we have found analytically the functions describing the ball's position and velocity components as a function of time. We can now use these results to answer the questions we posed. First, when does the object reach the maximum height? The condition on this is that at the maximum height, the object transitions from rising to falling, meaning its y component of velocity is 0. So, applying this condition in our expression for the y component of the velocity, we can solve for the time when the maximum height occurs, t max. If we plug in the numerical values, we find t max here, which is just what we found earlier with our computer calculation. So that's good. Next, for part B, we can find the height of the object at that time by evaluating our expression for y sub t at t equals t max. We do this symbolically first, and when we do the algebra, we obtain this result, which, when we plug in our numerical values, gives us pretty much what we found from our computer solution. Finally, to determine part C, how far the object has moved horizontally by time t max, we evaluate our function for x of t at t equals t max. Here's the symbolic solution, and when we evaluate, we find x is just the same value as we found in our computer solution. Let's close this lecture with a brief discussion about what would be needed to solve analytically for the object's motion with both weight and drag forces. As we discussed before, we now have two forces, weight and drag, that would add up to give the net force. So we need to start by re-examining Newton's second law. In fact, we would start with the principle in this form, where we will assume a drag force in the form we discussed earlier for our falling object. This vector equation is equivalent to two equations, one for each component. These expressions are examples of equations known as differential equations. We would need to solve these to find the expressions for the velocity, and then, from those solutions, do additional integrations to find the x and y positions as a function of time. The math here is doable, but it's a bit more involved than what is typically expected in an introductory physics course. Again, if we use the computer to help us do the math, with the problem involving both weight and drag, we can then focus on the most important part, the physics that's required to understand and to predict motion in real-world problems with realistic effects like air resistance.